Concrete example of this interesting problem that involves a finite sum. Let's just for the sake of shorter calculation, let's do n equals 3. Okay, so for n equals 3, if you substitute n equals 3 right here, I believe you get 7. That would be 9 minus 6 plus 1. So 9 minus 3 is 6 plus 1 is 7. Now if you substitute n equals 3 right here, you get 9 plus 3, that's 13, right? Okay, so we want to sum up all the even numbers between these two odd numbers, all right? And so those numbers would be 8. 8's between 7 and 13, 10 and 12, right? So it's a sum. Now what does that equal to, folks? When you sum that up, you get what? 18 plus 12, you get 30, right? So 30 is the sum. But of course, that's just a special case. Now we're looking for a closed form that involves n that's going to solve this. So let's take a look at how the proof of this might go. Now notice that both of these numbers are odd. We probably shouldn't be laboring the point too much, but just right here, if you factor out an n, you get n times n plus 1. Now consecutive natural numbers have the property that they have a different parity, but one of them has to be odd, the other has to be even. It can be the first or the second, right? So n times n plus 1 is definitely even, plus 1 would be odd. And a similar argument right over here, right? Again, if n were odd, n plus 1 would be even. If n were even, then done, right? Okay, let's move along. This is the odd number, so the even number after it would be achieved by adding 1. So that's where you get the plus 2. So that's the smallest even number between the two bounds. And then when you subtract off 1 from the larger number, you just get n squared plus n. Now that's important because we can sum between those values, right? Okay, so notice that we start with the smallest, which is given right here, and we end with the largest, which is given right here, right? Okay, now this is kind of fun how this works out. Now this next step is slightly unmotivated, but we did it sort of with the intent. You see, if we added the 2n in here, so you still have the very same thing. 2n minus n still gives you the n, right? Now, why did we do that? Well, that's because we can get a summation that involves n copies of n squared minus n. You see, you have n squared minus n here, n squared minus n here, n squared minus n squared minus n, and it's n times. You see, this is a key step right here. So these right here, 1, 2, 3, n of them, right? So that takes care of quite a bit of this above equivalent statement, right? Now what about the rest of this? We'll see we have multiples of 2 in here. Okay, we have multiples of 2 in here, and so we factor that 2 out. All right. Now we're kind of saved here because notice that this piece right here is a very well-known formula called the triangular numbers. In other words, inside the parentheses, these numbers sum to n times n plus 1. That proof isn't too difficult. We'll just state it as a fact here. These are called triangular numbers. N times n plus 1 over 2. But notice that's going to cancel with this 2 right here. And so we'll just end up with, okay, you'll end up with n cubed. Okay, I'm just multiplying out this piece right here, minus n squared. Okay, that's, again, all I'm doing is just multiplying out this piece of it right here so far. Now, the cool thing here, again, this 2 cancels this 2. And so you would end up with an n squared plus n right here. So you would have plus, see again, I hate to belabor the point, but the 2's cancel. And so you get n squared plus n. And so, y'all, this works out very nicely because we get our kind of a nice little closed form result. We get n cubed plus n. I love this. I mean, this kind of stuff is, I enjoy this, the purity of the discreteness of the natural numbers. No weird properties, limits, in construction of irrational numbers and stuff like that. So n cubed plus n is the result here. Now let's just check it. Let's just check it out though. Let's see. So we got n cubed plus n up here. So remember, I don't have it all on one screen, but okay, the result is going to be n cubed plus n. So let's see if that lines up with this. Okay, so this would be equal to, remember we picked 3, right? This would be equal to 3 cubed plus 3, right? Pretty slick, huh, folks? Okay, and that does equal to 30, right? Whoops. And it would have been kind of hard to guess that, I think, at the beginning. We got 30 just by concretely doing it, but this is 27 plus 3 is 30, right? So that checks. Now, also, I have another one down here for you guys that's kind of a larger number here. Now, we picked n equals 4 and we get 13, and 21 is the lower and upper bounds. So what will we have right here? We would have what? 14 plus 16, plus 18 plus 20. Plus 18 plus 20. Okay, now ladies and gentlemen, what is that? Let's see, I'm getting, this part is 30, 48 equals 68. And again, this is just a check on something we're pretty sure is true. But notice that does equal, the 68 does equal to 4 cubed plus, 4 cubed plus 4. Wow, neato bandito, all right. 64 and 4 is 68. So that checks also. And we've accomplished what we set out to prove. Again, this is the final result, n cubed plus n. And so the answer to the question up here would just be n cubed plus n. I like that one.